In this video, we're going to pick up where we left off in the last one, talking about linear regression line, the line of best fit, and what can we do with that. So we had been working with a set of data that was looking at the weight of a car in hundreds of pounds and the miles per gallon that that car got. We took a look at the relationship on the scatter diagram. We found out it was a strong negative linear correlation between the two variables. And then we found this line, y hat equals 43.33 minus 0.60x. And we want to talk about some of the features of this line. What exactly do these two numeric values mean, and what can we use this line to do? So, we had y hat approximately equal to 43.33 minus 0.60x. And here our x was referring to the weight of a car in hundreds of pounds. And the y, in this case this is a predicted y, this is a y hat, so this is predicted mpg, miles per gallon. What this line does, this line of best fit, is it allows us to put x values in. We can put in weights of the car, and we can find the predicted mileage per gallon for a car of that weight. Okay, so that's what the line allows us to do. It allows us to predict y's based on x's. It does not allow us to predict x's based on y's. We cannot put y values in here and predict x. It's the y that's got the hat. The x does not. Okay. So, a couple of things. First, let's talk about interpreting slope and intercept. Let's talk about the intercept first. So this part, the 43.33, that is the y coordinate of the y-intercept. And your book calls that value lowercase letter a. And what this means is that any of these lines that we look at are going to go through the point 0a. So the line goes through 0a. And you can see if we put 0 in for x, this term would drop out, and y hat would be this a value. So in this case, that means that our line would go through 0, 43.33. The x value here again refers to the weight, and the y value refers to the miles per gallon. Now, just because you are able to numerically interpret the slope or the intercept doesn't necessarily mean that that value would make sense in context. Here, what this point would actually be telling us is that a car that didn't weigh anything would have 43.33 miles to the gallon. Clearly, that's not an accurate figure. A car that doesn't weigh anything isn't going to go, so it's not going to get any miles per gallon. Okay, so sometimes these are just an artifact of the line. It makes the line fit well, but it doesn't actually necessarily make sense in the context of the problem. So this does imply that a car with 0 weight gets 43.33 mpg, which makes no real world sense. Sometimes those values will make sense. In this case, we had one that did not. But that, nonetheless, would be the interpretation of predicted. So we can see that's just not a very accurate prediction. Okay. Then, if we come back up here and look at the slope, that's this piece. That's the thing that your calculator will call b. And what slope is a rate of change. So slope measures the change in y, whatever your y variable is, for a 1 unit change in x. Frequently you hear this referred to as rise over run. Rise is measuring the change in y, right, the change in the vertical. Run is measuring the change in x, or the change in the horizontal. So slope measures the change in y for a 1 unit change in x. Those of you who have taken calculus will recognize this as dy dx. So it's our rate of change here. So in this case, our slope, the b value, was negative 0.60. And if it makes you more comfortable, you can put that over 1. This guy, again, is representing change in y. This guy is representing change in x. Since our y variable is predicted miles per gallon here, and our x variable is hundreds of pounds, here's what we are in fact saying. Here's how we would interpret this in the context of this particular application. For a 1 unit, so 100 pound, because that would be 1 x unit since x is measured in hundreds of pounds. For a 100 pound increase in a car's weight, there is a predicted decrease. Since the b value is negative, it's a decrease. If this were positive, it would be an increase. But there's a predicted decrease of 0.60 in the car's miles per gallon. Here, please note, you do want to say it's a predicted decrease or increase. You don't want to say a 100-pound increase in a car's weight causes a decrease of 0.6 in the car's miles per gallon. Remember, we talked in the previous video about how correlation is not causation. We can show that there's a relationship between the two variables. This describes some of the nature of that relationship, but you cannot imply that that relationship is causal. Okay, it's not as though that decrease is solely due necessarily to the increase in weight. There could be other factors involved. Okay. So that's how you would interpret slope and intercept. And then there's one other useful thing that we can do with the line of best fit. We can use it to make predictions. So making predictions. Let's say I wanted to know what is the likely number of miles per gallon that a car will get if it weighs 2,500 pounds. Whoops. What is the likely miles per gallon that a car weighing 2,500 pounds will get? Okay, so let's say that was the question I was trying to answer. Well, that's exactly what my line will help me with, right? 43.33 minus 0.60x. Here I can put in the weight. Here I get out the predicted miles per gallon. That is exactly what my line is set up to do. I put in a weight, I get out a predicted number of miles per gallon. So weight is going to go in here. Miles per gallon is what I will get out. Since the weight was measured in hundreds of pounds, what we'll be putting into here is 25, right? Because that's 2,500 pounds. So the weight in hundreds of pounds will be 25 right here. We'll get out the predicted miles per gallon. So we do y hat, approximately 43.33 minus 0.60 times 25. Crunch that through in the calculator. And we get approximately 28.33 miles per gallon. Okay, so that's our prediction. 28.33 miles per gallon. Now, we could ask ourselves, how accurate do we expect this prediction to be? And there are essentially two things that determine how accurate we expect that prediction to be. One is, how well does the line fit the data? Okay, if the line does not fit the data particularly well, then we have no reason to expect that a prediction made on an ill-fitting line will actually be accurate. Turns out there is a way to quantify how well the line fits the data. It's a value called r squared, and we'll talk about that in the next video. So hold off on this question for just a second. We'll come back to it. But the second thing that we want to look at when we're talking about how accurate do we expect a prediction to be based on a line is we want to look at, are we extrapolating or interpolating? Extrapolating is risky, interpolating is safe. So let's talk about what each of these terms mean. We extrapolate when we predict y values for x values outside of the domain of the original data and we interpolate when we predict y values for x values within the domain of the original data. So let's talk about the prediction that we just made. Were we extrapolating versus interpolating? If we go back to our original data set, way back here, right, that was looking at weight and miles per gallon, our lowest weight here was, what did we say? It was 23, and our highest weight was 52. So the domain of this data set is 23 to 52. Okay. So anytime we put a line into, or I'm sorry, a value into our prediction line, into our least squares line for x that is between 23 and 52, we are interpolating. We are predicting a y value for an x value that's within this window, essentially, this original realm of the data. If, on the other hand, we wanted to put in an x value that was way outside of the range of that, or sorry, the domain of that original data set, way over here, for example, we don't know what the line would do over there because we didn't collect any data in that region. That's called extrapolating. That would be making a big assumption that this line continues to hold for data values over here, and we don't know that because we didn't collect any data in that range. Okay? So here, with the value that we just calculated a prediction for a car that weighs 2,500 pounds. That is within the domain of this original data set. That is interpolating. That is a safe thing to do. And as long as the line fits the data well, we then would expect that to be an accurate prediction. So again, we'll talk about determining how well the line fits in the next video. But here we would expect this to be an accurate prediction. If, on the other hand, I asked you to make a prediction for the miles per gallon for a car that weighs 6,000 pounds, well, we didn't have any data going out that far. So I don't know if this line is valid for data values in that area. And so that would be risky. It's possible that it would be a decent prediction, but we wouldn't know that. Okay? But again, two things to consider. Are we extrapolating or interpolating? Interpolating safe, extrapolating risky, but also how well does the line fit? So you'll want to take a look at the next video for that discussion.